Hey guys, I'm Chandler Johnson, and I'm really excited to share with you all the little bit of information that I've learned, especially from our first hemodynamics lecture on Poiseuille's law as well as Ohm's law. And because I'm one of the first few people to post on this forum, my task is to relate the diameter of a certain vessel to flow rate using Poiseuille's law. So before I address Poiseuille's law, which is right here on top, I'd like to talk about Ohm's law. So Ohm's law is equal to delta P equals F times R. So delta P is going to be our change in hydrostatic pressure is equal to F. So that is equal to flow times R, which is our resistance. And resistance can also be related to this little equation right here. Resistance equals K, our constant, which is actually 8 over pi, coming from our diameter of a circle over r to the fourth power. So going back to Ohm's law, we can see that this was actually expanded upon by Poiseuille above to have R incorporate the viscosity as well as R, the little r, which is going to be our radius. So first of all, I'd like to kind of just give a mathematical example before I get into my physical example. So in terms of radius, just generally we know from our lecture that when you have a larger radius and subsequently a larger diameter, you will have a greater rate of flow. So that's going to be our F. But like, why is that? So it's because if you rearrange this equation, you have F, also known as Q, our flow rate, is equal to your delta P divided by resistance. If you have a smaller resistance, you will subsequently have a greater flow rate just because your resistance is going to be on the denominator. If you have a smaller number on the denominator, then you will have a larger number overall as compared to a different number that has like a greater denominator, just by kind of like dimensional analysis. So anyways, getting back to the radius and the diameter. So in like a given vessel or tube, if you have this larger diameter, you will have a larger flow rate. And in turn, if you have a smaller radius, smaller diameter, you will have a lesser flow rate. It's going to be a smaller number. And why is that? That's because you're going to have more friction against the walls of the vessel, which will in turn slow the flow rate, give you a smaller number. So let's go ahead and get into this example that I have right here. So just, chatting a little bit more in terms of Poiseuille's law, when you have this equation, it's really important that your tubes are the same length because that is one of our variables that we want to maintain constant. So as we can see, I have my tubes that are the same length here approximately. I know this is a little bit longer, but just for convenience sake, we're going to kind of assume that these are very close. It's not just like a crazy amount of difference. So I have my two tubes here. My fluid here is going to be water. It's going to have the same viscosity constant. We have I'm looking at this equation by the way. We have our constant that is going to remain constant, of course. What is going to change right here is the radius of the tube. So I'll show you guys really quick. I have this red tube, which has a smaller diameter than my larger clear tube. I'm trying to like show it to y'all. So I have this one that has a larger diameter. So let's go ahead and inject. I have this, constant volume. That's not part of the equation, but I think it's just to make it look a little less misleading in my demonstration. So what I'm going to do is go ahead and put some water in my syringe. It's actually like a turkey baster, I think that's what you call it. And then I'm going to go ahead and take my smaller radius, smaller diameter tube, and kind of show you guys the fluid flow real quick. So here we go. I'm going to inject it, and you can kind of watch for the rate of fluid flow out of the tube. Here we go. Okay, that's the first example. I'm trying to ensure that the change in pressure is going to be similar between the two examples and having the plunger of the syringe move in at kind of the same rate, so the same delta P. So let me repeat the example with the larger radius tube just for y'all's viewing pleasure. Here we go, larger diameter tube. I'm going to inject, and again, y'all can observe the rate of flow. So I hope you guys were able to notice and observe that for the same delta P, same viscosity, approximately same length, the change in flow, or our flow rate, was higher in the larger diameter tube. But that is basically my example. I hope you guys enjoyed, and good luck studying. Hope you had a great Monday. Thanks so much.